But really excited to hear this one. Thanks everybody for joining us today. We got an exciting lunch and learn. I think it's be something a little different for us. Today we have Morgane McKibben and Emil Charrington from NASA's Plankton Aerosol Cloud Ocean Ecosystem, or PACE Observatory. They're going to talk to us a little bit about the PACE mission and learn about some of their data products and how they can be applied to a range of on-the-ground applications. So yeah, let's turn it over to them.
All right. Hello. Well, I will be going first today. Let me get my screen in order. So hello, everybody. Thanks for having me today. Apparently my slide doesn't have my name on it. My name is Morgane McKibben. I am the PACE applications lead for the PACE mission. That means I'm in charge of our applications program, which I'll explain in just in just a second. For today's talk, I'm going to talk a bit about our mission. Why would anybody, be interested in PACE? I'm going to talk about our applications program, and then I have a little bit about GIS and PACE and what I would love to hear from you guys. So first of all, why PACE? Kind of if you take any big level ideas away from this talk today, I would love it if you took these with you. So PACE is really the only satellite in the NASA fleet to provide near daily global hyperspectral observations of Earth. We'll see examples of what that means in a second. PACE has a really unique combined technology and coverage among all public and private satellites that are currently in flight. We have a hyperspectral sensor that sees the Earth in a broad range of light, as well as 2 polarimeters, which give us interesting information about our atmosphere. All of the things that PACE provides, all of our data products, are multidisciplinary. This means we have a comprehensive set of products for ocean, land, air, inland waters, etc. We're really excited because PACE is fueling new scientific breakthroughs, enabling new practical tools to support society from PACE. So stepping back a little bit and kind of giving you the big picture, this is a timeline of NASA's Earth fleet. So basically, what is in orbit right now? These are the oldest satellites in the middle, kind of spiraling out here to PACE as one of the newest ones in orbit. Kind of what the takeaway is here is that we've had NASA's had an Earth observation fleet for decades. And each time a new sensor goes up, it's usually got some kind of innovation that is pushing the boundaries of what the Earth fleet can already do. And that's very much what PACE has been doing with its hyperspectral information. Let's go into a few details about the mission. We were launched just February of 2024. We released our first data in April. There's 3 instruments aboard, a hyperspectral radiometer called OCI, and 2 polarimeters, HARP2 and SPEX1. PACE is able to see the entire world continuously, flying over most all places in the world at about 1 o'clock local time. It's a 3-year mission. And of course, our data products, as with all NASA data products, are free and open to everybody. And why was PACE launched? It was launched to advance and extend the ocean, biological, ecological data records, as well as looking at our clouds, looking at aerosols in the atmosphere, and also collecting terrestrial data. This may be more information than you all want about the instruments. I'll go over it kind of quickly. What is the Ocean Color instrument? It was designed at NASA Goddard Space Flight Center, where we who work for PACE are located. It's a hyperspectral scanning radiometer. These are its specs. It can see hyperspectrally from the UV through the near infrared with a 5 nanometer bandwidth. As I mentioned, it takes about 1 to 2 days to span the globe, and it gives us 1.2 kilometers square resolution. We also have the 2 polarimeters, one of which, HARP2, is hyperangular. That's its specialty. So it's looking in a whole bunch of different angles at the Earth. And the other one is hyperspectral. So it's looking in, maybe 5 angles of the Earth, but with the full spectral resolution. A lot of times when we talk about PACE, it's mostly referring to the Ocean Color instrument. That's going to be true for a lot of the talk today, because this was the, mission prime instrument. The other ones were added on as well. So As far as the data products, as I already mentioned, they're comprehensive. We have a lot of data products for land, sea, and air, and inland waters. We carry both advanced products that only PACE can provide, as well as heritage ones. So if any of you are familiar with satellite remote sensing, heritage missions like MODIS, we are able to carry on a lot of those products as well. We don't have time to go into all the products. If you're interested, please feel free to go check out this data table. It lists in more detail than anyone could ask for every data product that we have currently and plan to release in the future. So, kind of reiterating what I was saying earlier, the big deal about PACE, we see invisible, microscopic, even microscopic stuff from space, and we see it in an all new light. For our eyes, looking at the Earth from space looks something like this, right? We see a beautiful blue planet, clouds, and we see the land. Well, there's tons of microscopic phytoplankton, which is what a lot of these images are of. They're basically the microalgae of the sea. They're the food or the plants of the sea that kind of basically feed everything else in the ocean, as well as those of us that eat seafood. And we can see them from space because there's so many of them. We can also see aerosols, another kind of particle. But in the atmosphere, we can see aerosols from space. There's a few of those in the pictures here, like, salts in the air or pollens or different kinds of particulates from fires. And kind of the big, the big takeaway from that is PACE is going from being previous sensors like MODIS were multispectral. That means that they had, if you imagine it like crayons, the satellite could see the Earth in maybe 5 to 8 colors. That's it. Now with PACE, we can see across the entire UV to visible to near infrared spectrum in full color. And we also have 7 shortwave infrared bands, which isn't quite shown here. But the takeaway is this is a huge leap in coverage. More spectral coverage means more stuff visible from space. Here's an example that gets oceanographers like me very excited. This is a PACE first. This is showing those algae I mentioned a minute ago from space, which we've been able to do for decades. But this is doing something new. This is splitting them into 3 groups indicated by the 3 different colors. This is something new that PACE can do and is extremely exciting. This is our first product to do so. And it's splitting. And, the reason we care about this is, if you think about it, this is food for fisheries, right? What kind of phytoplankton is there can help you decide what kind of fish might be there. It can also help us with, better quantifying, climate interactions with the air. Because phytoplankton are so critical to the Earth as photosynthesizers, being able to tell who is there, which phytoplankton are there, is going to greatly advance our understanding of the Earth system. Here's another example that we really love to show, this time on land. So this is kind of a similar idea. In the decades before PACE, we had those multispectral missions that saw a few colors, 5, 8, something like that, colors in the visible spectrum. And with that, we could look at something like normalized difference vegetation index. What this basically is it's asking the question, how green are the plants on land? Kind of how green and bright are they? And it's using, just kind of a couple bands, maybe 2 bands of information, one in the visible, one in the near infrared, based on brightness. So we've been using this for decades, and it tells us, kind of what's growing where, or whether there's vegetation growing. And sorry, I messed up here we go. Whereas in contrast, PACE, we can now see that same terrestrial vegetation, not just that it's there and that has been more of it, there's growth, but now we can start to see with all the different colors of the rainbow, which plants are there and get insight also into their health. And this is because the different pigments that plants make, in addition to green chlorophyll, which most of us are familiar with, carotenoids and anthocyanins are also made by plants. And the ratios of all these pigments to each other can tell us something about which plants are there and also possibly what their health may be. So, this figure on the right is giving us a huge wealth of dense information about that vegetation on land compared to the one on the left. Very much the same story as the phytoplankton in the sea. And that's because we're talking in both of these examples about photosynthesizers. So they have pigments that change in response to their environment and which types are present. Kind of bringing together the why PACE idea again. So as a NASA mission, this is an innovative mission. It's kind of pushing the envelope, as I mentioned. And another way that PACE is, kind of pushing the envelope is it was really the first NASA Earth observation mission that integrated an applications program into the mission from when the mission started. So this mission started in 2014, and they started thinking about the applications or kind of on the ground, decision-making type of uses for PACE from the time they started building it, and have been promoting and working with folks ever since to basically kind of see what we can do to make the mission be as applicable to on the ground applications and use as it is to, kind of the foundational research science that these NASA missions always advance. And why would we do that? It's because, as I kind of just said, it increases this value of Earth observations for, kind of using things for day-to-day information and decision-making. So that's going to bring me into PACE applications. That's leading me into our applications program, which is the program that I lead. And just like PACE, just like the PACE data products, our applications program supports across sector and across aquatic, land, and atmospheric domains. So this might mean, we help folks with, better viewing disasters with PACE data, or better seeing water quality information with PACE data. We can see oil leaks. We are able to close huge uncertainty gaps in the climate record with some of our atmospheric products. We can look into harmful algal blooms. I'll give you examples of all of those in just a minute, but there's a lot of applications of PACE data because of its broad coverage. And, kind of as I've already said, applications are basically defined by it in our world as, kind of using the satellite data in some kind of on the ground, decision-making need that really helps, provide some practical solutions. Applied research is really that bridge between, an idea or of a foundational science advance found through research, bridging that with how we can put that into action on the ground. And we work with a huge range of end user communities. It could be individuals and groups, public and private sectors, national, international, and from local to global scales. And our goal with the PACE applications program is really translating this groundbreaking science of PACE into on-the-ground action. We do it by building new partnerships between the data producers and science and across sectors, and also even among Earth observation missions. We work to ensure the accessibility, usability, and actionability of PACE data, which means basically we help people be able to find it and use it, which makes it more useful. And we also work to demonstrate and quantify the societal value of the applications of PACE. How about some examples? All right, what's PACE doing? So PACE, so the coastlines, the inland Great Lakes, basically what some call the ocean economy or the blue economy, are huge for the United States. They add at least $370 billion to our GDP. And the plankton I was talking about earlier, the phytoplankton, they're super important, right? Along all these coastal waters and the inland Great Lakes. They're in all surface waters, and they support all the aquatic life. And PACE is able to provide that technology I was showing in the last slides about seeing more information about plankton, which we're looking forward to using to improve responsiveness of fisheries to always changing ocean conditions and also changes in the phytoplankton types, and also helping to better identify harmful algal blooms from space and better identify the environment that, aquaculture farms or other, shellfish harvesting or coastal recreation. It's really important to know where harmful algal blooms are in those kinds of areas. And PACE is able to better see them. We'll see some examples in just a second. Another way that PACE is supporting on-the-ground applications with our land information, as I was mentioning earlier, we're providing, we're adding to decades of, folks in the agricultural field have been using satellite data of the land, like that product I showed earlier, for decades. And now PACE, we're hoping to bring new information to farmers, forestry managers, or anyone in the land monitoring and management realm on maybe better calculating plant growth. That's pretty critical to things like crop yield, or to see how plants are thriving or not. New insights into their health, the health of the vegetation, as well as new ways to identify plant type and land cover, land use changes. PACE is also supporting air quality monitoring from space. And this is because, PACE can see the air in the clouds with kind of an unmatched, really unique data set. And this can support disaster response to wildfires, volcanic eruptions, which is really critical to aviation. We get better weather and air visibility forecasts. The data can be imported or pulled into different models to help improve those models and forecasts. And we have several partners on the ground that are working to see how they can improve air quality and pollen monitoring and forecasting, which are important to public health, by using PACE data. I was going to show you an example of one of our newest partners working with us. I don't know where this slide is here instead. Talking about how that health and air quality, this is basically reiterating what I said about ways that we're using PACE for health and air quality. But this new partner that I was going to show you is from the Georgia Department of the Environment. And he, like you guys, is a GIS user and was really excited to see that we have a brand new nitrogen dioxide product from PACE that is higher spatial resolution than other nitrogen dioxide products. So he's a new partner with us, and kind of in your guys' area. With a similar background, that is looking to use PACE to improve their ability to monitor and forecast air quality across the state of Georgia. Another example of partners, or this is another early adopter that we're working with. We have a group that's looking at water quality for aquaculture health and suitability, kind of off the coast of Louisiana. And the issue here, the thing is that they're looking at is aquaculture. In order for you to grow a big swath of oysters like they might do down here in the southern tip of Louisiana, which is what this map is showing in some of these pictures, it's important to know about the environment. And there was an unexplained die-off in 2020 that was accompanied by cyanobacterial harmful algae or an algal bloom. And they suspect, well, maybe that's what caused it. And PACE, their group is working to identify specifically that type of algae using PACE data. And this is the first image that I'm aware of where anyone was able to specifically identify cyanobacterial blooms off the coast of Louisiana, which could help, if you can see where those cyanobacteria are, that's really useful for the on-the-ground and how it's changing each day. That's really useful for those aquaculture farmers in terms of, deciding on their response to that. Also, I'm not also pretty much in your neck of the woods, like along the Gulf Coast and also the eastern Florida coast. There's a lot, there can be large sargassum events. And these events, they can cost tens to hundreds of millions of dollars in lost tourism, cleanup, infrastructure damage, and even the commercial and recreational fisheries losses. This is where there's just feet of seaweed that end up on the shore, and then it just rots. And it causes a huge mess. If you leave it there, it causes gases that make people cough. It's these kinds of events are increasing in frequency because the sargassum belt across the Atlantic Ocean is now basically a persistent feature. And every now and then it will come rolling from south, kind of the mid-Atlantic up to up into the Gulf Coast. So we have a group working with us. They're early adopters and science applications team members that work with us to use PACE's spectral capabilities. This is a plot basically showing you what I was mentioning earlier, where previous satellites saw these gray bars, like MODIS. MODIS could see these kind of broad, 1, 2, 3, 4, 5, about 8 or 9 colors. In contrast, these green and brown lines are showing you all the spectral information across the wavelengths from blue out into the reds and the near infrared that PACE can see. So this is so much more information. This is a graphic of what I was talking about in terms of, the actual colors being seen by PACE. And you can see there's a big difference between this line, identifying the different, kind of phytoplankton types that we can see with PACE that we couldn't see before. They're taking these advanced capabilities of PACE and they're incorporating them into their Sargassum Watch system. It's a dashboard they've had for many years that lots of stakeholders use in order to help improve early warnings of, sargassum coming towards their area. So I also wanted to make sure that today I talked a little bit about how you can join us all. So if you're interested in the PACE mission, if you'd like to learn more or just kind of keep up with our, what we are up to, we have a community of practice. And this really supports everybody across research and applications domains, really anybody interested in the PACE mission. This is where we send all of our news, our events. We have a quarterly newsletter as well. And we connect everybody through an email list. If you'd like to join us, please do. This QR code will take you to the instructions to join. And also, I'm particularly interested to see if any of you would want to join us as early adopters or applications partners. These are folks that we partner with across sectors to do that co-development of PACE applications capabilities. I'll go over the details on the next slide. If you're interested, be sure to reach out and email me. So as I said, our applications partners are cross-sector, and we're really looking for folks that are wanting to integrate PACE data into decision-making, business, resource management, etc. The partnership with PACE is a non-funded partnership where we specifically work with you to help you accelerate, translating the PACE observations that we're pulling down at NASA into the kind of action that might suit your work. If any of you have applied products or projects with direct health, economic, or other benefits to society, please consider joining us. Or if you aren't sure if you qualify or not, just send me an email. You can also see this webpage here to see examples of what folks are doing with PACE data and find our application form. All right, so ending here, I actually have one more slide left on PACE data and GIS. This says GEE too, but this is just on GIS. Emil will be talking about GEE. Entering the world of GIS is new for me as a scientist, as well as for a lot of the folks in our group at NASA. Traditionally for research science, for the kind of data that's been served by our group over the last several decades, we put the data out there on NASA websites, and typically, researchers or whoever else needs it comes and gets it. There wasn't really a strong bridge with the GIS community. Not to say you can't use the data in GIS, you absolutely can, but there's not really, even to this day, there's not a really strong direct pipeline that takes the NASA data over to places like Esri's Living Atlas. So this is something I'm working hard to change with the PACE mission, is to do what I can to get PACE data served to more GIS folks. I'm excited to say that in later this year or early next year, we're going to have 10 imagery services for 10 of our different products, some ocean, land, and atmosphere products. They're all going to be available on Esri's Living Atlas. And this is made possible by working between myself, our Earth Data GIS folks at NASA that kind of do the pipeline that pulls the data from the NASA side to the Esri side, as well as folks at Esri have been wonderful working with us on doing this. I also want to say, and so those products will all be kind of flat products of quantifiable things like amount of phytoplankton or a type of, amount of nitrogen dioxide in the air. They won't be the hyperspectral data. They're from the hyperspectral data. I want to also say that we're really excited that ArcGIS, with their last several successive releases, they've been improving their hyperspectral support each time. And with their upcoming version 3.6 release of ArcGIS, they're going to have even stronger hyperspectral support. And we're working with them to create basically a PACE story map where they use PACE hyperspectral data to help demonstrate these new features for version 3.6. So I'm pretty excited about that. This means that we'll have, both just, kind of data products that are ready to go being served by Living Atlas, and also a tutorial on how folks can dive into the hyperspectral data with ArcGIS if they're interested in that. So I would love to hear from you guys also as GIS users. I'm really interested in hearing from GIS communities what people need. As I mentioned, I don't have a GIS background. My background is in MATLAB, Python, those kinds of coding, and kind of a research background with those are the ways I accessed satellite data. So I don't know if any of you have. I would love to hear from you on what kind of services you need, if the PACE data is interesting or useful to your work at all, or any kind of information you might want to provide as a GIS user. You can feel free to reach out to me. You can ask questions if there's time after this talk, and also feel free to reach out to me by email. This again is a QR code to sign up for our mailing list, and I'll put the link in the chat also when after I'm done with the talk. That's what I've got for today, and that was I'm glad to take any questions.
That's really cool, Morgan. I'm just curious if you guys have any applications or have any maybe initial thoughts of ways the PACE data could be used for like identifying chemical concentrations either in land or in air. Like, I don't know, one of the things that comes to mind is like mercury in fish.
We could not see mercury in fish. That wouldn't be something that we could help with, because it has to be something that's kind of on the surface with some kind of optical signature. And with the mercury being in the fish, we couldn't really tell that it was there. But what a lot of folks do is there's different research of different types. I don't know about one with mercury specifically, but to get at questions like this, they'll do things like use the satellite data to identify certain water conditions that are associated with whatever they're after. So I don't know if folks are doing that kind of research, but no, we couldn't see mercury in fish directly. The the capabilities of us to see, kind of doing through the imaging spectroscopy of, minerals on the Earth. I don't really, I don't know much about that. I don't know if we have the right spectra in the right regions, but I do know that we are getting, information on trace gases with PACE. So kind of that's the nitrogen dioxide or the ozone in the air, or the particulates in the air. We're getting information on those, but not so much specific, I don't know, chemicals of interest. I'm not sure what work is being done in that realm or could be done.
Sure. Thanks for that.
Mm-hmm.
I'm just wondering if there are additional questions for Morgan. If not, I guess I have just a few slides, and I guess also I wanted to leave some time for additional questions as people kind of ruminate on what Morgan presented, and guess what I'll be presenting as well. Any more questions? If not, I guess I'll start sharing my screen.
Yeah, go for it, Emil.
Thank you. And also I just pop my camera on just for a moment, just to say hello to everybody, and just to say that for me, it's an honor to be able to present to the GIS Association of Alabama, having lived here for, I guess now going on almost 10 years. So again, thank you, Justin, for the opportunity to share with the community here. And I know that you're recording this, and so I guess an additional number of folks who couldn't make it today will be able to see this afterwards. And of course, thank you to my colleague Morgan for kicking this off and sharing that really great information about PACE itself. I will drop my camera now. But I guess also just to say, as kind of like the two-parter of this, and I guess maybe first off to say thank you to Justin for promoting me to to being a part of the PACE team. Just kidding. So I'm not, so Morgan is the mission applications leader as mentioned. I guess I don't have a formal role with the PACE group, except as an early adopter. And while Morgan is based out of NASA Goddard, I'm based here at the University of Alabama in Huntsville, and through the cooperative agreement of our university with NASA, I support a new activity called NASA Earthrise, and also like to recognize some of my colleagues who I see here in the virtual room. So I guess with that, just like to, basically I'd like to talk a little bit about kind of like a plug-in set of work that we've been adding on to some of the PACE data that Morgan showed, and how folks here can hopefully also access data in a different way. Again, I just have a few slides, kind of, this is the overview of what that's supposed to be. But to kind of add on to what Morgan said, maybe just to back up just a wee bit, NASA, starting in 2000, had a hyperspectral sensor that was called Hyperion, that was on the Earth Observing 1 satellite, which stopped operating or was decommissioned back in 2017. In addition to that, back in 2022, NASA launched the EMIT sensor or instrument that is on the ISS, the International Space Station. And as Morgan mentioned, just last year, or I guess maybe 18, 19 months ago, the PACE satellite launched. And as she, well said before, it has this ocean color instrument, the OCI, which is this hyperspectral sensor, and just kind of comparing how OCI stacks up or compares with Hyperion or EMIT. It might not have the spatial resolution that Hyperion or EMIT have, but the one, the thing that's really the cat's meow is that OCI is daily, whereas Hyperion, EMIT didn't have the ability to capture the same place every single day. And in terms of the different things that are out there, also just to highlight that there are other hyperspectral missions, instruments that have been launched. But the one, I'd say, unique thing about the NASA hyperspectral instruments is NASA's open data policy means that the data from Hyperion, EMIT, and PACE are freely available, and some of the other data sets come from commercial companies and essentially have to be purchased. And as Morgan, one of the last things she highlighted, the partnership with Esri, again, noting that a bunch of folks here in this virtual room are, users of Esri platforms like ArcGIS, ArcGIS Pro, etc. That also opens up the possibilities for being able to access PACE data that way. I guess I'm not going to rehash some of the things that Morgan highlighted, but I guess my mind was really blown. I got to meet Morgan in person, attending a PACE community meeting that was organized in December last year. And again, I had heard about the PACE mission. It's called the Plankton Aerosol Cloud Ocean Ecosystem Mission. And so I didn't think that it had a whole lot to do with land. And, my mind was blown at that meeting. It was highlighted, well, actually, PACE is collecting data over, the entire Earth's surface, and obviously grabbing a lot of land. Here's a slide from Morgan from a few months back, and highlighting some of the different indices that are being generated. And again, for those of y'all in the community who, you've worked with things like NDVI or EVI, these different vegetation indices, a lot of these shouldn't be unfamiliar to you. And as Morgan also highlighted before, that there are also some unique hyperspectrally enabled indices that are only possible from the different thin hyperspectral bands that PACE and similar sensors can generate. And I guess with that, kind of diving in. So most of us based here physically in Alabama, and beyond PACE being having data every single day, one of the cool things is, if you use a portal that NASA has called NASA Worldview, you can, every single day, you can log in and see what, PACE imagery over the state of Alabama and other places looks like. And so here is PACE imagery for the state of Alabama just yesterday. And that's, say, Worldview is kind of one way to see the data. And of course, as Morgan was getting at, if you're interested in then pulling down the data and working with it in your desktop GIS systems, for instance, you can grab it from this other platform from NASA called Earth Data Search, where you can download the data as different granules. They're in NetCDF format, which I think speaking for other GIS users to say that that CDF is kind of wonky. It can be converted to GeoTIFF, but yeah. NASA also has something called the Ocean Biology DAC, where you can also find, there's this dedicated section just for grabbing PACE data, seeing that, and again, you can grab those data sets. And then I just wanted to highlight here kind of what some of the different PACE products that you might be able to pull from, say, the OBDAC or the NASA Earth Data portal, how heavy those are, because kind of leading me to the next points that I'm going to be making. And so this data comes in different spatial resolutions. So as Morgane said before, I guess the finest spatial resolution of the PACE data, or its original spatial resolution, is something along the lines of 1.2 kilometers, which might be considered, coarse depending on the scale that you're working at. But that said, when these data sets have, over 100 bands, if we grab the data, for instance, at 2 kilometer spatial resolution out of the OBDAC portal, a single granule that you're going to get, which covers the whole globe, is something like, over 30 gigabytes just for a single file. And when you consider that these files are being generated on a daily basis, it's quite a lot to download. Or you can grab the data at 4 kilometer spatial resolution, which comes out to just under 7 gigabytes, or 0.1 degrees, which is something like 10 to 11 kilometer spatial resolution. Then that is 1 gigabyte. But again, the trick is one of the neat things with PACE, because we're getting the data on a daily basis, and the PACE team is generating these also at, say, different time steps, at, say, 8 days, every month, etc. Then again, you're still talking about a lot of data to work with. So that said, those of us here at the University of Alabama in Huntsville, and also I think a lot of folks at NASA work with, or have worked with, a platform called Google Earth Engine. I know Justin at the top of the hour was mentioning his experience with it, etc. Just because the data in PACE are big, platforms like Google Earth Engine, and I'm not here to say use Google Earth Engine or use any specific commercial or cloud-based platform, but the idea of these are that instead of downloading a whole lot of data, you can work with that data in the cloud. And so again, PACE data are huge, as just highlighted, and so GE, as well as other platforms, facilitates the work of working with that data, as well as Earth Engine itself, say, has access to catalogs of other data sets like EMIT, JEDI, which is a spaceborne LiDAR instrument, MODIS, which is a multispectral sensor that's also collecting every single day, etc. And then by developing this toolkit, which is, again, the work that I'm presenting on and done in collaboration with other colleagues, including in consultation with Morgane, the idea was that we could, through this toolkit, provide folks with tools for how to interact with that PACE data. So not just being able to see it, but also being able to work with that. So one of the things that we're able to do through Google Earth Engine is, I guess, similar to some of the other things like from NASA Earth Data Search, visualize that data, but also, as I'll highlight in just a bit, other functions for working with that. So this is just showing you, one of these mosaics from June of this year, kind of seeing what you're seeing. And of course, for some of the areas where it seems like you're seeing it kind of splotchy, it's because PACE is an optical sensor. If there are clouds, then it will miss data. Thankfully, for Alabama, for the most part, the monthly data sets seem to, help us to overcome that issue of clouds, because the clouds move around. So if you're averaging data over a whole month, you're going to get a pretty decent view of the state of Alabama. This one, I guess I won't kind of hover on too much, but just to say the work that we've been doing with the toolkit, we've kind of been doing some behind-the-scenes work of setting up pipelines for grabbing PACE data from NASA servers, pulling those down, actually converting them into GeoTIFFs, and then taking those GeoTIFF data sets and putting them into Earth Engine to then make them more easily accessible for the set of folks who use Earth Engine. So what is the toolkit really? It's set of functions for data discovery, data visualization, time series analysis, gap filling, image classification, and so for instance, there's one of the scripts that we have there, an example over Huntsville, Alabama, just kind of gives you for a given, you plop down a point and it'll tell you the different data sets which are there. Say one's the most recent imagery that's available, et cetera, et cetera. But not just PACE, but also some of the other ones. Also for viewing images, and so there are scripts there that allow you to say zoom into all of the U.S. or specifically the state of Alabama and see what's there. Another one then extracting spectral signatures, and again I think some of the folks on this call should be familiar with the concept of spectral signatures. And so, like Morgana was highlighting before, if we're dealing with data like from MODIS that only has 6 bands, essentially, for you plop down a point, you're only going to get data on the different wavelengths, the specific wavelengths that MODIS can see, which are blue, green, red, near infrared, one short wave wavelength, and another short wave wavelength. And so this is, for instance, if we were to take MODIS data over the same periods that PACE has access to, so 18 months of data from March of last year to August of this year, this is what MODIS data would look like. However, with PACE, we're going to see these signatures that look much more detailed. And as Morgana was getting at, there are folks who are starting to do research on this type of data would be really useful for looking at, say, types of crops, types of vegetation, and different sorts of things if we're looking at land data. Another part of the toolkit is, again, being able to plop down points, in this case, Montesano State Park, not too far from where I and other colleagues are based, and be able to see how these different indices kind of behave in time. And again, the neat thing is some of these indices can't be generated using the normal sources of data that people might be used to, like the data from the commercial satellites that generally are covering only visible and near infrared, or even things like Landsat or MODIS or VIIRS or Sentinel-2, which again don't give you that hyperspectral perspective. Another part of the toolkit has to do with filling of gaps using different, again, time series functions actually to fill the time series, but also image classifications. So again, pretty sure that you GIS folks in the audience familiar with, again, taking satellite data and generating maps of land cover based on those. And so here, for instance, is a sample output over the state of Alabama looking at last month's, not last month's, but the August PACE mosaic, and then turning that into a map of land cover, again, highlighting the things that the 122 bands that PACE is seeing. I guess to start to wrap up, just to give us some time to chat about it, what's in the toolkit, and I'll share a link to the toolkit in Earth Engine in just a wee bit. But the idea is that we have these dependency packages that kind of have different equations for generating vegetation indices. They have information about the different bands of the OCI, the Ocean Color Instrument, combinations that allow you to view the imagery in specific ways like false color, natural color, etc., as well as a data loader package that's pulling in data for the continental U.S., other sites in other parts of the world like Mesoamerica, also the global data sets, the vegetation indices at the 8-day and monthly timescales, and then just some sample sites that can be also used in combination with the functions and the data sets themselves. I guess more of the same, just to say that through the toolkit, we've been kind of playing a game of catch up of grabbing the data as they're released. So in terms of data over the continental US, including the state of Alabama, 18 months worth of data at different spatial resolutions from that, say, finer 2-kilometer product that they put out there, as well as the 1.2-kilometer daily data sets that are there, grabbing them for specific spots, as well as the global products, etc. And I guess also just to say that the vegetation index data, which folks might be interested in, and which are also going to be accessible through that ArcGIS plugin that Morgane mentioned. That is updated every 8 days, as well as monthly, but we're grabbing the 8-day data just because it's quite a bit for us to grab the daily data. And then, yeah, integrating, or we've already integrated 2-kilometer data, pulling in select 1.2-kilometer data, and also to say that in discussions with Google, since we're running this stuff through Earth Engine, they've indicated an interest in the future, likely after the PACE products move from provisional to final status, to actually ingest all the data themselves. I guess I have a super short demo to show, but I guess I'd like to share this link in the chat, if you give me just a moment so I can copy that out and post that in the chat. Again, for folks who already have Earth Engine accounts, and if not, should be fairly simple for folks to sign up for an Earth Engine account. Let me post that. I also see other cool things that Morgan has shared in the chat. Let's see. Okay, looks like I've stopped sharing altogether. So if you give me one moment, let me just share again. Let's see. Here we go. So I guess before I guess turning it over to questions, like to mention that again, the toolkit, as mentioned before, is basically just a set of tools or scripts from Google Earth Engine, which will then, you can launch a script. Again, not sure how familiar folks are with Earth Engine, but the idea is you have these scripts that you click on them, hit run, and it will launch all of the features, etc. And here, for instance, is one from the set of classification tools. It just provides the example for different types of classifications for the state of Alabama, using unsupervised classification, using different classes. And I guess not to belabor the point, as mentioned before, examples for looking at time series analysis, including the one over Montesano State Park, generating the spectral indices like what I shared on the slides, discovering data, and visualizing the different data sets that are there. One of the scripts that's there, for instance, basically will just show that it takes the monthly data and just does an animation of the monthly data over Alabama, just so folks can kind of see what the data like is there. And of course, if you click on a given point, you can then pull up spectral signatures. And I guess maybe also to mention, and there's a link in there as well as in the PowerPoint, and I'll show the slides afterwards, for being able to view the PACE data and on the fly click different points and generate spectral signatures. And I should mention that this was also based off of work done by a colleague and friend, Dr. Sam Roy from Spatial Bytes, formerly of Maxar and formerly of Planet. We were able to take his code and repurpose it for PACE data. And I guess the last thing I'd like to mention is we do have a GitHub page for the PACE toolkit. I can also share this link in the chat before I stop sharing. The PACE toolkit GitHub page basically just gives a summary of some of the same things that I've mentioned before, as well as links to different resources, including work from the PACE land data users group that Morgan and other colleagues lead, and other types of resources. So I guess with that, we are now at 10 to the top of the hour, and I guess I can stop sharing and I guess open it up back to questions. So thanks again, Justin and everybody. And I know it's lunchtime, and so maybe folks are hungry, but not sure if folks might have questions for me, or you thought about additional questions for Morgan.
Yeah, I don't really have a question. I just again, I think it's really cool. A lot of great data out of there.
And I guess maybe if I could throw a question to you, Justin, as the president of the GISAA, I guess it would be useful for probably for Mergain, as well as my other colleagues who are here on the line, kind of how you see imagery being, I guess, imagery on a whole. So not just hyperspectral imagery, but how important access to imagery is for, I guess, maybe different members of the GISAA. You talked about at the top of the call, you were highlighting that the GIS Association of Alabama has a lot of municipal type users, and so I'm wondering if you might maybe tell us a little bit more about that. And I guess again also to highlight that some of my other colleagues from NASA Earthrise and the University of Alabama also joined as audience members, so it'd be useful for them to hear too.
Right. Yeah. It's, obviously I don't work in the municipal arena. I'm in environmental sciences. I think, like I mentioned earlier, in environmental engineering. And, from my point of view, it's incredibly, valuable. I get asked all the time, what's the most recent imagery, like, because we want to look at, pre and post construction type things and stuff like that. So, without speaking for everyone, I think access and availability to good quality imagery and data is vital for all things GIS. Really, I don't know if others on the call want to jump in with an answer.
Yeah, I'll throw some out there. Hi, Emil. My name's Joshua Chris. I'm the GIS manager for Jefferson County, Alabama, and the past president of GISAA. So we fly 3-inch true color orthophotography on an annual basis for the county. We also run a GIS consortium made up of about 14 or 15 partner agencies. So for us, that is the most critical part, is the orthophotography. So that feeds the background of critical applications that we use for work orders, permitting, like CityWorks and Acela. But we also serve that up to our emergency services partners. So Jefferson County 911, Birmingham 911, and others use that orthophotography as backgrounds for their maps. And then we use that for essentially to support our Board of Equalization for appraisals. So they look at parcels, we look at buildings that have been amended, newly constructed, or demolished, and then we cross-reference that to parcels, and we provide that over to our Board of Equalization for appraisals. So we get a lot of use out of it. We also get a NDVI and a fourth band, which we don't do a ton with, but we also are moving into 3D, but really using some LiDAR data that we had collected last year for that. So, but it is critical for us and multiple agencies, and I think most municipalities, county governments would also say that it's critical. It just comes down to a funding issue.
Awesome. Thank you, Joshua, for sharing, and of course, thank you, Justin. And no, I wondering if Morgan, might you have questions for Justin or Joshua or others?
I was just really curious about what folks in here do. Like, if it's a super, it sounds like, I bet, like, are people super local level? Does anybody use any satellite data for anything in GIS for your various, uses? I'm just really wanting to understand how folks, at the state and county and lower level, those kinds of scales use GIS information, and where different kinds of satellite data may or may not fit into that.
Yeah, hi, this is Josh again. I'll just give from my experience, and I've just been in public service for about 4 years, but been doing GIS for about 18 years. So in most of my experience, I haven't used a ton of satellite imagery. We've done some vegetation classifications and land use analysis, but GISAA is made up of a lot of the public sector, and we have some contacts in forestry and some of those other kind of departments, and I think they have a lot more use cases. I also have a friend of mine I graduated with who works for a paper company, and so they're constantly looking for new satellite imagery to look at potential lots or areas of land that they want to harvest, or also monitoring areas where they planted trees. So I think it's a mixed bag. I would think most people typically on the call are probably in the public sector. And so for me personally, we do anything from deploying apps and servers to databases to drawing in, planimetric, vector-based data. It kind of spans the gambit. So I wouldn't say it's not valuable by any account. It just depends on kind of which industry that you're in.
Thank you for that.
Yeah, I tend to echo what Josh was saying there, and again, for me, I do a lot of work with land cover classifications, habitat suitability modeling, things of that sort. So I just know I'm really excited to get into the toolkit and see what data is there and how I can leverage it more.
Yeah, thank you, Justin. And I guess just wondering quickly, and hopefully I'm not putting him on the spot. Jacob, he's a colleague of mine. I was wondering if and he was recently doing some work looking at
from the Forestry Commission.
Or no, I guess Abby, please go ahead if you have a question.
No,
Yeah.
your question, like we use quite a bit of sentinel imagery. I have those in our web maps to where people actually, that's been like, especially the last 2 years, we've had dramatic southern pine beetle infestation, and sentinel imagery has really helped us. And also, every once in a while, I'll use GE to clip images, disturbance data, and stuff like that. So yeah, forestry does use your data quite a bit, and it's been really very helpful.
Awesome. And what sector do you work in, Abby?
I work with the Alabama Forestry Commission, and I do GIS here.
Awesome. I hope you don't mind. We might want to follow up with you offline. And I guess, Jacob, since I was kind of teeing you up, I don't know if in the next minute we have or something, if you wanted to mention anything about some of the work we've been doing, Jacob.
Sure thing. Thanks, Emil. And it was good to hear about that, Abby. It would be great to connect. I work at UH with Emil, and I've been looking into monitoring southern pine beetle, mostly in Alabama as well as Mississippi and Georgia in the last few months. Looking at sentinel imagery as well, like you had mentioned, as well as planet, as well as some Landsat, and doing some more general timberland monitoring as well, looking at change over time to see harvesting patterns, age of plantations across the state, and potentially look at thinning, commercial thinning behavior. So it would be really great to discuss at some point that with you and with the Forestry Commission, and kind of see where we can go from there. That would be really interesting.
Thank you, Jacob. Thank you, Abby. And of course, thank you so much, Morgane, for road showing it with us. And of course, thank you, Justin, for accepting the when we reached out and said, hey, would this be a possibility?
Yeah, we definitely appreciate you both and all that you guys are doing for the community. Real quick, one thing I forgot to mention at the top of the Lunch and Learn, Josh pinned a link to a survey 123. It's real quick, it's just a few questions. We're interested in knowing where you guys are joining us from today. We don't share any hyper specific location information with others. It's just kind of for internal planning. So if you could take a look at the chat and fill out our quick survey, that would be awesome. And just keep a lookout. We do have a few more Lunch and Learns that are planned upcoming, so details about those will be coming out in the next couple of days and weeks.
Thank you again, Justin.
Yeah, thanks, y'all.